This conference will now be recorded.
Hello everyone, welcome to our webinar on evaluating transformer designs with electromagnetics simulations. My name is Arfad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at COMSOL and how to set up physics for transformers and evaluating parameters of its design. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. So what is COMSOL Multiphysics? COMSOL is a multiphysics modeling, simulation, and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers, to post-processing, to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you have completed your COMSOL simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And with the new product, the COMSOL compiler, you can also create standalone applications. And today we are focusing on the features of the AC/DC module. When you expand COMSOL Multiphysics with the AC/DC module, you unlock features for specialized low-frequency electromagnetics modeling in addition to the core functionality of the COMSOL Multiphysics software platform. And if we look into the landing page of the AC/DC module, we can see what you can do with the AC/DC module and what is available there. So you can create simulations for transformers. That's today's webinar core focus. And you can extract the lumped parameters of it, but there are much more on top of transformer design. You can create Joule heating effects. You can investigate these in COMSOL Multiphysics, and there are predefined physics interfaces for coupling together different effects like thermal expansion and heat generation by conduction. The first demo is a transformer, an E-core transformer design. We have some specifications from the specification sheet of the product, and we want to simulate it in COMSOL Multiphysics. And for that, we need to take into account some portions of the model, and there are lots of insignificant details that can be neglected, and we should neglect during the simulation of such a design in COMSOL Multiphysics. Because we could end up with a very, very dense mesh with lots of degrees of freedom, and for various reasons, this is unnecessary for us. So we will remove some details and we further simplify the geometry, the coil design also, and we will use a SPICE list to connect the finite element model to an external excitation voltage source, and both for the primary and the secondary side we will connect some resistances in series. So this example demonstrates how to perform transient simulations of single-phase E-core transformer Including the effect of a nonlinear BH curve in the soft iron core, the model computes the spatial distribution of the magnetic and electric fields, the magnetic saturation effect, the transient response, and the flux leakage to the surroundings. And this nonlinear BH curve includes saturation effects that is used to simulate magnetic behavior of the soft iron core. Hysteresis effects in the core are neglected. The model assumes that the primary and secondary windings are made of thin wire and have multiple turns, using the assumptions that the wire diameter is less than the skin depth and there are many turns. These windings are modeled with the coil feature. Furthermore, the model does not account for eddy currents in the individual turns of the coil. The primary winding is connected to a primary resistor, RP, as you can see in the figure, and the AC voltage source, while the secondary winding is connected to the secondary load resistor, RS, as shown in the figure. The model is solved in the time domain for a line frequency of 50 Hz. Several important design parameters, such as the magnitude of the input voltage, the line frequency, the number of turns in the coils, and the coil resistance, are parameterized and can therefore easily be changed. And if we jump into COMSOL Multiphysics, we will start with a predefined and preprocessed geometry to speed up the computation. So I will open up that one. So here the geometry is predefined and the physics interfaces are also connected and added, but we need to further investigate the boundary conditions. So we have parameters for the primary and the secondary side, the number of turns for the primary and the secondary side, the line frequency and the line voltage also. And to defining the physics, first we should assign the materials. So we add air as the surrounding domain, and we will add the soft iron without losses. So this assignment goes to the core, to the magnetic core. So here we assigned this soft iron material. From the magnetic fields interface, we will add an Ampere's law for the nonlinear core. So we select the core domain only, and from the material model, we change this relation to BH curve. So if we go back to our material selection, we will see that we have this BH curve predefined, and if we plot this, we can see what will be used during the simulation. So this is our BH curve behavior that will be used during the solution. So we have defined the BH relation for the core, and we need to define the two coils with the coil feature. So we select those domains are predefined, so we can choose from the selection the primary winding. That's the inner one. So we will use a homogenized multi-turn feature with a numeric coil type, and we connect this to the spice list. So it connects to a circuit, and it says we need to connect an external I versus U. So if we go to the settings, we have this external I versus U, where we can simply connect the source to our coil. So now we have the excitation on the primary side. So this is connected, and the number of turns, it's a parameter, number of turns on the primary side, so it's NP. We duplicate this, and we change the primary winding to the secondary one, and then we changed the number of turns to number of secondary, so it's NS. And we need to connect also to the secondary side with an external I versus U. So we connect this to the secondary side of our list. Okay, and we need to indicate the input for the boundary where the current flows on at which boundary. So for the primary side, we select this boundary. So from this console, we'll know how the current flows in the primary winding, and we need to do the same for the secondary winding. We need to select that little boundary. So this is the input side. So we have the BH defined internal core. We have the two coils, one for the primary, one for the secondary. And for stabilization, we need to apply a so-called gauge fixing for A field that's needed for numerical stabilization. That's it. We have the materials. We have the core. Everything else is defined as an air. And we have some study nodes. So there are several study nodes. The first one is a so-called coil geometry analysis. It means we need this study step to calculate the direction of the current flow in COMSOL Multiphysics. And then it will be used as an initial condition for the stationary and or the time-dependent solvers. So at study 2, we have a time-dependent solvers. We are solving for 15 milliseconds to look how the current flows in each coils and what happens with the saturation and the magnetization in the core. And as you can see, what we've solved in study 1. So we use the solution of the coil geometry analysis. So that's how you can handle coil setups in COMSOL Multiphysics. It takes some time to solve. So I open up this already solved model and we can look into the results, how they look like. So this is the same setup. So we have two 3D plots, one for the magnetization and one for the current density. So we need to change some logarithmic factors to decrease these arrows to make it smaller. Okay, so this indicates the current flowing in our coils, and the surface plot is the flux density norm in Teslas. And of course, we can jump between different time stamps, so we can go to the initial time step and everything is 0, and then as we are evaluating in time, the density is changing and also the saturation and the cross section. And for that we can since it's a time dependent model, we can create an animation. It makes more sense to visualize the time history of the magnetization here inside the core, so we can make it to repeat. So that's a single phase transformer design in COMSOL Multiphysics, but you can also include and incorporate much more complicated designs like a 3-phase transformer. This is our next example. You can see, and you will see the links later, and you will get the PDFs in the follow-up email. So this is the 3-phase study case. We have the primary and secondary windings, and you can see the number of turns and other parameters of the model. This is the layout, so you can see that the core is laminated. We will use a nonlinear BH curve for that purpose, and we will have some plot results. So you can see the saturation and the magnetization in this one 3D domain. And if we go into COMSOL, we will see how it's set up. So it's pretty much the same. So we will use the coil feature, but we have, of course, more coils since it's a three-phase design with a more complex geometry, but on the boundary settings, nothing special. So from the magnetic fields physics interface, we have these primary coils, 3 of them and 3 other on the lower side for the 3 phases, and the inner parts are belonging to the secondary winding. There are 3 of them for the 3 phases, and below them there are 3 others. So these are the windings for the primary and for the secondary coils, since it's a pretty nice and simple boundary condition how you define coils in COMSOL Multiphysics. For the outer metal part, we use an impedance boundary condition. There are 2 different scenarios, an open circuit test and a closed circuit test. So there are 2 other domain definitions for the core, and these will be switched on or off depending on which kind of study you are performing, whether it's an open circuit test or a short circuit test. So if we go into the study nodes, we can see it's a frequency domain study for 50 Hertz, that's the line frequency. And in COMSOL Multiphysics here, you can simply switch on and off boundary and or domain settings. And for the open circuit test, we use the last settings for the core, and for the short circuit test, we use the second one. So we switch off, so we disable the last domain setting for the magnetic core, which is, if we go into that, it uses the same HB curve relation that we defined previously. So we will use that material behavior here in this 3-phase coil design. And if we go to the results, we can see that that's the density norm for the open circuit design. For the 50 Hertz line voltage, of course, you can perform different frequency calculations or different phase calculations. We can see the saturations at the cores. We can see how the current flows on the carpentry. So we can see some inside. We can have a look at a know-how on how these transformers perform and behave. And we can also plot the saturation, what we have seen on the slide. And what's more important is plotting the losses in the carpentry, and it's a frequency domain study. So here on the horizontal axis, you can see the line frequency, the excitation frequency, and you can see how the losses are going up with higher and higher frequencies. You can see more details, much more details and descriptions at COMSOL's website. So you can go to the applications website and you can look into the documentation itself. So if we go into that, you can have a detailed look how it's set up, what is an open or short circuit test and how it is performed, and how you implement that in COMSOL Multiphysics. And you can also see another study, a 2D study, where the coils are detailed and they are examined and simulated in details, not as a homogenized multi-turn coils, but each individual wire is simulated and looked into how the losses affect the overall performance. So you can see more details and you can read more details here at the website. You will get the links in the follow-up email, and you can also try out these applications yourself, how you can do whether a 3-phase or a single-phase simulation of transformers in COMSOL Multiphysics. And for that, I wrap up my demo. And if you need more information or you need some assistance, how you can do such simulations in COMSOL Multiphysics, feel free to contact us and visit our website for more details. And see you at our next webinar. So I thank you for your attention. That's all for today.